Welcome back, mineralogy fans. Oxygen may be the most common anion with a -2 charge, and we've seen sulfur be the -2 anion for many other minerals when oxygen is absent. But what about the -1 halide anions like chlorine, fluorine, bromine, and iodine? Minerals that bind cations with these halide anions are the halide minerals. And the most common by far is halite, NaCl, or common table salt. And the name comes from the Greek hals, meaning salt. As a mineral, halite has a vitreous to greasy luster. Having a density of 2.17, it is a little lighter than most minerals. It has a cubic crystal habit and cubic cleavage, that is, 3 directions of cleavage at right angles. Don't trust the color at all in these because, as disconcerting as the thought of black, blue, or pink salt may seem to us, nature has no problem making the stuff. It's a softer mineral at 2.5, about the same as your fingernail, and some samples will even fluoresce. Obviously, the most diagnostic property is the taste. We all know what salt tastes like. The level of taste is due to the solubility of halite. It easily dissolves into water, and also easily precipitates out of water. Because the two most common elements dissolved in seawater are sodium and chlorine, salt is the most common evaporite mineral to come out of dissolving seawater. The weak nature of halite and its relatively low density and the fact that large beds of it can deposit out in areas where seawater consistently undergoes high evaporation all work together to mean that these large salt beds, when buried under other rocks with a higher average density, will begin to flow and in cases begin to thicken and rise to the surface, deforming the overlying rocks in the process, forming salt diapirs. Where the salt thins or dissolves out, the underlying beds are deformed in a different way. The beauty of the landscape around Moab and Arches National Park in Utah and Canyonlands are in great part due to this ductile property of the paradox salt formation below. The upthrusting salt diapirs also make what are known as traps for petroleum underground, and some of the first oil wells ever drilled were around salt domes. With all that salt is to us in our lives, loves, and literature, I will not belabor the uses of salt, but will say that when our future alien, robot, reptilian, zombie overlords take over and force you to work in the mines, just beg to go work in the salt mines. With salt rising up towards the surface, they can be easily accessed from above, and huge, well-ventilated rooms are excavated out with large, structurally sound pillars left behind that you can drive trucks through. Now, just don't get turned into a pillar of salt. But if you do, maybe get turned into a pillar of Sylvite salt. NaCl is halite salt, KCl is Sylvite salt. Because these two minerals are isomorphic, meaning different chemistry but the same crystal habit, all the physical properties that apply to halite apply to Sylvite, though pink to red colors are more common in Sylvite, and the taste is like a bitter salt. The principal uses of Sylvite are as a source of potassium for fertilizer and as a salt substitute for those who need to lower their sodium intake. And most people who do have to take salt substitute complain about its bitter taste. Halite is one of the first minerals to precipitate out of seawater, and Sylvite is one of the last. So you tend to find it where the driest seabeds were once disappearing. Moving on from chlorine to fluorine, we see that most of this element ends up binding with calcium as CaF2 or fluorite, sometimes and more in the past called fluorspar. One might think the name comes from the fact that fluorite tends to fluoresce, but it's really the other way around. Fluorite gets its name from the Latin verbs fluere and fluor, meaning to flow, and that refers to the use of this mineral in metallurgy as a refractory mineral to lower the viscosity of ore material. Because fluorites also commonly fluoresce with ultraviolet light, it gave its name to that phenomenon, and later Sir Humphrey Davy named the element fluorine that was found in fluorite, and the common -1 anion fluorine is called fluoride. Okay, fluorite has a vitreous luster with a tendency to twin in complex ways, and with a density of 3.1 to 3.2, a little denser than average, which is one way to tell it from quartz, but fluorite also has cleavage. In fact, fluorite has 4 directions of cleavage. Fluorite's four cleavage planes allow the crystals to be cut into the pyramidal four-sided die and octahedral eight-sided die shapes, though it does scratch rather easily. Like calcite, it shows birefringence in some thin sheets. That's the rainbow diffusion of light as we saw in calcite, but fluorite will not effervesce and is harder than calcite, being the Mohs scale marker for 4. Fluorite, with 4 directions of cleavage, has a hardness of 4, but when it comes to color, there is even more. The clarity of fluorite can be stunning, the colors so variant that it is a prized display mineral, though too soft for gems of regular use. But their clarity, refractory ability, and 4 directions of cleavage means they can be cut into beautiful pieces. As mentioned in its name, it is a refractory mineral for metallurgy, but also for ceramics. We actually speak of metallurgical, ceramic, and acid-grade fluorites in increasing purity of CaF2. Though some samples of fluorite are less transparent, the most clear specimens have been used as lenses and optics for various instruments. And any industrial process that uses fluorine, such as the making of hydrofluoric acid, comes from fluorite. Fluorite can form in open spaces, vugs as we call them, in the carbonate rocks like limestone and dolomite where the fluorine can combine with the abundant calcium. But fluorite also forms with the previously mentioned sulfide minerals in hydrothermal systems, and so are associated with some of the more valuable hydrothermal metal deposits. As with all other mineral groups, there are less common forms out there like carnallite, the KMgCl halide with its stunning transparency and tendency to decay as it absorbs water from the air, or atacamite, which is a beautiful green vitreous copper chlorine halide. And so we come to the end of the halide minerals, and I hope you realize what that means when we come back next time. When we return, it'll be time to meet our last major mineral group, the native elements.